Thank you. So, it's okay. Thanks. It's a great pleasure to be here, and thank organizers for inviting me to give a talk today. Okay. So we are try to try to make talk a little bit more general. Okay. So I start with So first, let me just recall a very rather classical theorem in the sense. So it's in many textbooks. So it's called a Bishop-Gromov volume comparison. So if you let M and G be a Riemannian manifold or dimension n, suppose a Ricci curvature bigger equal to 0, then you have this volume comparison. Namely, look at and geodesic ball of radius r, and then divide by r to n. So this ratio is monotonic decreasing with r. Okay, so this plays an important role in the recent developments, or actually in many developments in geometric analysis. For instance, and it's used in proving existence of tangent cones by Chigger Cody in their regularity theory. So this is analytically, this volume comparison basically equivalent to this. If you look at R to be a distance function from a given point, x is any point in the M, then this is less equal to R in the sense of distributions, in a weak sense. Okay, so this is equivalent to volume comparison. So it's we just put it in a more geometric way, but it's analytically it's just same as these things here. So this I don't know. It works. That's okay. So now to me, so that's just simple starting. So now let's consider this closed manifold as before. I don't know why I put dimension m now. It's anyway, it's n. So Ricci flow is introduced by Richard Hamilton in 1982. So I put in this form. It's slightly different from Richard's case because he put 2 here, but that's it doesn't matter because this is up to rechange time. The reparameterize time. This is constant in front of Ricci curvature can be made to be any positive constant. So I don't know. Anyway. Okay, so from early 80s to 90s, many powerful analytical tools in the Ricci curvature for Ricci flow has been developed by Richard Hamilton and others. And for example, the maximum principle for tensors. For example, if you want to study this geometric flow like Ricci flow, you compute how curvature evolves, because that's a very fundamental things in the geometry. So you look at the Ricci flow, look at how metric evolve along the Ricci flow. You by looking at how curvature evolve. So then you want to check certain curvature properties are preserved. So also like differential hierarchy inequalities. That's like control curvature at a given place. Giving point by curvature at a different moment. So anyway, and also derivative estimate of curvature and so on. So they are also introduced certain tools, analytical tools like Chigger-Gromov convergence theorem and so on. So however, Ricci flow may develop a singularity at finite time. So in order to apply Ricci flow to, for example, to solving a geometrization conjecture for 3 manifolds, one needs to show that a finite time singularity can form only along the sphere instead of homogeneous Riemann surfaces. Actually, Hamilton already ruled out the possibility of you do a surgery along the Riemann surface of high genus. So one essential point to remove is the following. So there is a very simple solution called a cigar solution. So this is just on R2, for example. R2, and look at this metric. Of course, this metric does not depend on T. It's a static metric. But what you can do is you look at this metric. This suppose this G, and the reach of this G you compute is equal to a Hessian of F equal to 0, where F is minus log of 1 plus square plus y square. Okay, so this is this metric satisfies this equation. So then you use a gradient flow of F, and then the gradient flow produce a family of diffeomorphisms, and you pull back this metric. So that's give you a solution of Ricci flow. It's called self-similar solutions, okay, or soliton type solutions. And this solution has so it's it's called a cigar solution because it's when you go to approach infinities, it's almost approach to a cylinder. So the cross section is a circle, okay, and if you look at the gradient flow, or maybe minus gradient flow given by F, the effect of this family diffeomorphism is just a push, like pull back this push back of this cigar from infinity towards this. And by doing this, you make a curvature around here is bigger and bigger. So this might be a singular and answers for singularities at finite time. But of course, it's two-dimensional. But then you can cross with S1, it becomes a three-dimensional picture. Okay, it becomes a three-dimensional solution, and then the cross section is given by torus. Okay, so and this is a solution of Ricci flow. And this is very classical solution. I mean, very, it's a kind of soliton type solution for Ricci flow. So you basically, for a long time, you try to remove this to disprove this solution cannot be as ansatz for finite time singularity for Ricci flow, starting on a closed manifold. Of course, this is on a non-compact manifold. Okay, so this is for this program, or this Hamilton's program for solving a geometrization conjecture. This is a crucial point because if this solution can be a finite time singularities, or can be model of finite time singularities, and this approach fails because we know for any three manifold, if you how do I say, you start with S3. You take out some link and look at do surgery along this tubular labyrinth of the link. You can get any three manifold. Okay, so doing a surgery along the tori, basically you cannot say anything about topology. So this is a crucial thing to prove. This cannot occur as a finite time singularities. So that's what the breakthrough Perelman did in 2002. So to prove this, he needs this so-called volume comparison theorem, okay, or volume estimate, as he phrased as a so-called non-collapsing estimate, okay. So Perelman has two versions of this no local collapsing theorem, which was derived by monotonicity of either entropy or reduced volume, two things. So the first one, and the statement is a bit easy. So it basically says if M is closed, if you have finite time singularity along the flow, then this flow is not locally non-collapsing. So by that we mean the following things. Okay, the statement of theorem is short, but you have to phrase this. So this means if it is locally collapsing means what? If we means if there's a sequence of time goes to this capital T, if this sequence of metrics, a sequence of metric balls at the time tk, such that they don't worry about these things. This is just kind of keep certain scaling things. And if a curvature is bounded at this scale, then the volume goes to 0. Okay, so this is a typical collapsing case, because if you look at this solution here, as xy goes to infinity, this is almost like this metric. This is like cylinder metric. So cylinder metric is flat, and so this actually goes to flat exponentially, and yet the volume is not like Euclidean, because cylinder volume is if you look at the ball of radius r is linear, is at order of linear r. So it's if you're shrinking this r at certain scale, this is a collapsing case. So this is if you take xk goes to infinity, this is actual collapsing case. So these paramount things exactly can be used to exclude this. Okay, and actually the proof of this used the so-called entropy things. So this theorem was proved by using a monotonicity of so-called entropy. So to recall what is entropy, we first recall the functional he introduced. So this is functional, okay, and that has a different form. So if I set u to be this form, and then you get the same functional in a different form. So if you look at this is this thing functional bounded from below exactly means you have a log Sobolev inequalities. Okay, and another way to say that is actually you can look at just on the Euclidean space or Rm. Okay, if you look at Rm on the Euclidean space, the heat kernel, standard heat kernel is the minimum of these functionals. Okay, these functionals. So then you can define the entropy, namely you fix the metric G, and you fix this constant, this parameter here. Then you minimize among the like finding eigenfunctions, eigenvalues. You minimize them among all these u with these normalizations. Then you get this entropy. Okay, and the key things he proved is this is non-decreasing along the Ricci flow, non-decreasing along. And then once you have this fact, it's basically a one-page proof to prove this is a non-collapsing theory. Okay, or maybe 2 pages. I think 1 page is enough for this original form. If 2 pages, you can weaken the curvature assumption. So which he didn't write in his paper. He communicated when he was visiting MIT. So anyway, so it's this factor. It was used to prove this theorem. I guess I have to come here to turn page back. So basically proved. To prove this theorem, then you can use this to rule out the possibility of this. Okay, so then the finite time singularity, he because of this, he assured all the surgery are done along S2s, along the topological S2s, or Z2 quotient of S2s. So okay, so this is the first version of that. So there is a second version he used. And it's this one looks longer, so maybe I draw a picture. So it's this. So this means basically following. You look at this the picture. You look at this. Suppose this is x-axis is denote your manifold, and this is your time. Okay. This time so you look at the 1 point x0, okay, and you look at the geodesic ball of a radius r0. So this is 2r0, okay, this x0. But then we look at the parabolic. So in the Paraman's original version, you look at the parabolic ball. So you look at this. Okay, so this is R0 square. So everything estimated should be scaling invariant. So we plot that's why we plot these scales here. So it's like a curvature is bounded like this. All the time goes to R0 square in comparable to radius. So then you look at here. Okay, so you look at another point which is pretty far, maybe from this x0. So this might be so that's from here to here might be A R0 order. So A could be very big. Okay, giving. So you look at a different point, and they look at the geodesic ball, the parabolic balls here. So you want to compare the, say, compare the volume of this geodesic ball. So this is radius r here. Okay, radius r here, and how do I say? So I want to estimate the volume of ball here from below by the order of r to n. Okay, so but you need some conditions. So the condition here is initially you have the condition in this ball. You have two things. The curvature is at this order, and the second thing, the volume is bounded from below. Okay, so volume at initially bounded from below by this order. Okay. Okay. So it cannot be the initial volume cannot be too small. Okay. So then here you also need conditions. So first is so here only condition is the curvature is less equal to r2 minus 2. Okay, r2 minus 2. So that's but this is on the ball of geodesic ball of this order. So this is r0, and this is this whole is r squared. The length, the size of this all time interval is r squared order. Okay, so then the conclusion is non-collapsing. So namely this ball here of g at r0 square at a different time is at least some kappa, some constant of r to n. I guess I used m here, sorry. Okay, I probably changed the, okay, so I guess n is m here, sorry. So this is basically Paraman's second theorem. And this theorem looks longer than before, but this has, maybe I'll tell you a difference. The second non-collapsing theorem, this is the one I just stated, was proved by using a monotonicity of reduced volume. I want to say about the reduced volume here, it's kind of like a parabolic version of volume, okay? And since I want to use that later, okay? And one remark I want to make is, though the second theorem, which I just stated, looks more restrictive because you have this curvature on the conditions on the parabolic ball, but it holds in the uniform way, okay? And it serves the same purpose in the Paraman's in the previous things, namely rule out this Cigar solution as a possibility for finite time singularities. You can use this to exclude that too. But this one has advantage, namely it holds in the uniform way. I mean, at least that's the way we stated it holds uniform way. And so when you try to solve the whole program, a whole generalization conjecture, or solving the Poincare conjecture, you need to consider, you need to do surgery. And after surgery, you need to consider a solution with surgery, namely the more complicated solution of Ricci flow. So in that case, this is more useful. I mean, this second version is more useful because it holds in a uniform way. Okay, so later on, and more recently, so it follows from Zhang Qi's work, and 2 years ago by rediscovered by Bing Wang, that on the parabolic ball, the condition can be weakened. Namely, this initial condition, this last condition here. So this condition can be replaced by scalar curvature to be bounded instead of whole sectional curvature. Okay, so the proof is also not only that you don't need to be on this parabolic slice. You only need to be on exactly this time slice. So this is also just on the time slice, BGR0 square of XR. Instead of here is a parabolic region. Okay, and the proof, what they did. Sorry. No, I guess let me just mention. I didn't write down. So the proof they used is they used the W function again. So the proof here in this Bing Wang, they used the local entropy. So basically localizing, which I will say more in the later, localizing Perelman's entropy. Okay, so it's different proof, but still using these tools. So what is our theorem? So early last year, we proved this theorem. So what we improved is just the following. We basically drop this condition. We don't need to assume this probably there's a low bound of volume. Okay, so low condition on that. And also, we replace this, just by Ricci curve. And this turns out in application is very useful. So, and also it's you don't need to be on So just replace this by Ricci curvature instead of full sectional curvature and no full conditions. Now, of course, then the conclusion is this is bounded from below by volume ratio at initially. Okay, so G0 of X0 R0 of R0M. Okay, so that's our theorem. Okay, that's our theorem. So this is what we call the relative volume comparison. So namely, or in other words, we know we got exactly how this low bound depends on initial volume. I mean, it's in the right scale. Okay, so the proof used the localized version of entropy instead of reduced volume as did by Perelman. Okay, so clearly our theorem generalizes Perelman's theorem since we do not assume any low bound on the volume of initial matrix. Okay, so the initial matrix may collapse, but we can still bound how the volume goes at a later time. Okay, so the constant here is kappa here can be made explicit, but it's not sharp, and the method we are using now, and we has no chance to getting a sharp kappa. Okay, so you might have must find more wonderful tools in order to get exactly kappa, which I don't know whether this precise kappa can exist. Certainly, it's what I try to say is still a question, because in a Bishop-Gromov, this volume ratio is monotonic decreasing, right? This BR XR of Rn is decreasing. Okay, so this in that case sense the kappa is 1. Okay, so in the Ricci flow case, we don't have that. Okay, so before I go tell a little bit about the proof, let me tell you why we came to this. So I do believe this relative volume comparison theory should have more applications, but this is one application I show you. Okay, so because this there are still many questions left for Ricci flow. For example, even though we know the three-dimensional case, the finite time surgery is done along S2 topologically, but we still don't know exactly how this finite time singularity is formed, or say is there a canonical model for finite time singularities. So whether this finite time singularity distance to a singular point is finite or not. Okay, so that's something we can still one can still study. Okay, so but I want to give an application which is relate to things I have been working on for last 10 years. So this is about the Keller-Ricci flow. So first, let's assume this. Oh, sorry. What is? Okay. Anyway, so an assume a manifold is Keller manifold, and then we know the Ricci flow preserve a so Ricci flow preserve these Kellerian conditions, so you get Ricci flow. So this is the exact original flow. Okay, so only write in terms of Keller form. Okay, so what's okay, anyway, so it was proved in the late 80s, this by Suji, and if a C1 is non-positive, then the Keller-Ricci flow has a global solution. Okay, so we clean up some of these details in the proof. So if a C1m is 0, then it follows a cos result that omega t converges to Calabi-Yau metric, and so we are interested in the asymptotic behavior of omega t in case of C1m is somewhere negative. Okay, so for this Keller-Ricci flow, what we are interested in is first, of course, we also need to understand the finite time singularities. That's correspond to this minimal model program, try to collapse contracting and parts of where the first Chern class is positive. But here involved, today I only more interested in a part after you find the minimal model, then the Ricci flow has a long-time solution. So we are interested in what kind of limit of this Ricci flow as time goes to infinity. Okay, so by our assumption, we can have a holomorphic. Let's have a holomorphic vibration. So from you are giving manifold into some projective space, such that the pullback of this this line bundle on the CPN is given by lective function, multiple of lective function class. So then we denote this to be image of pi, referred as Euro is called the canonical model of N. Okay, and the M0 can is a set of regular values of pi. Okay, and the quadratic dimension of M is simply a dimension of this image. Okay, so in our case now is chi pi is 1 to n. Okay, of course here is this is well known to many people. So our conjecture is regarding a Ricci flow is the following. So and above assumption, this sorry, there's -1. Okay, t -1. So we scale. Look at the t -1 omega t. Omega t is a solution of Ricci flow. So we concerned what's the limit. What's the limit as t goes to infinity? As t goes to infinity. Okay, so first is part we conjecture this converges in the Gromov-Hausdorff topology to a unique compact metric space. So it's homomorphic to a canonical model of that. So here is in the previous canonical model is constructed by algebraically through holomorphic sections. So here we want to say this in the metric sense, the limit is the same as so first term is the same as at least topologically same as the one constructed algebraically, and there is a smooth canonical metric on the regular part on the set of regular values, such that this metric, this distance function is induced by this smooth metric here. Okay, and of course, since we are talking about these metrics, we also hope this convergence on this part. On this part is in the nicer topology. So here I say at least a C0 topology, that's for certain. Of course, one might hope to be a better, stronger topology. So in general, we don't know. Okay. So maybe I read. Maybe a bit faster. So what we recall, we have this holomorphic map to a M canonical. Okay, and this I record here pi of a regular value of pi. Okay, and so of course this has a compact set. This has an open set M0 canonical. So I want to say on this part, convergence is actually more regular. It's more regular. Okay, so there have been many works on this conjecture. This conjecture was proposed a decade ago, and many was done. For example, it's if it's general type, then the chi pi, namely the quadratic dimension is n, then there is a canonical Cantor-Einstein metric, possibly singular. This was done before by Suji and also and myself with Zhang Zhou later on. And also we know the scalar curvature of this along the flow is uniformly bounded. I should say, sorry, it should be again. There's a error here. So it should be a scalar curvature of this. So second part should be a scalar curvature of a T inverse omega T is uniform bounded. Okay. So that's a sequence. I dropped this normalization here. Okay. So should be there's a normalization here. Okay. So this is some results we know, and more recently, if M is of general type, Jiang Song proved this has a bounded diameter and its metric completion coincide with omega can. Okay, and this Bing Wang used this to prove a diameter is uniformly bounded along the Ricci flow, so it converges to a compact metric space. In the Gromov-Haus topology. So it remains to prove, so in the case of general type, it remains to prove Z is homomorphic to a M canonical. And this should be true, okay, should be done, but it's not probably in the written form. To me, it's, we are more interested in the case when this quadratic dimension is between 0 and n. Okay, so this corresponds to a collapsing case at time infinity, which are more difficult to study. So in this case, so this time, this dimension of this is strictly less than dimension of that. So generic fibers, namely the fibers in this part, are given by Calabi-Yau manifolds. Okay, Calabi-Yau manifolds. So then, so this way we have a holomorphic map from the base, the regular part of base, into a moduli space. So this is simply mapping this, giving M canonical goes to a Calabi-Yau. So this simply giving any point here, just the pi inverse in this moduli space. Okay. So this is come to a new class of metrics, which we constructed a decade ago in 2007. We call it twisted Canaan-Einstein metrics. So this is called equation for called twisted Canaan-Einstein metrics. I guess I still took your background case. So especially one case, when the lambda is -1, so this existing twisted Canaan-Einstein metrics can be reduced to solving these complex Monchampy equations. Maybe I just so it's very much like Aubin-Yau's theorem. Okay, but except we have a less regular right-hand side. And indeed, in a few years ago, Jiang Song and I solved this equation and proved that there is a unique twisted Canaan-Einstein metric on any canonical models. Okay. So moreover, we also proved this is up to scaling this Ricci flow converges to this canonical metric on this part. Okay, but we only prove in a weak sense, namely in the Kähler potentials and the potentials, C alpha topology in Kähler potentials. Okay, so later Feng and Zhang Zhou is in Sydney improved the convergence to a C1 alpha topology on the potentials. So, but this is not strong enough, and this that's maybe I just say one thing is forget about this. So Tosadi, Vankov, Yang, and just 2 years ago or 3 years ago showed the metric, this normalized version, normalized the metric converges to a M canonical in the C0 topology. That's like for this part of on this part. Okay, so that's solved partially the conjecture I made. Okay, so if a generic fibers are flat, for example, like tori, So then they even proved the smooth convergence on this part. Okay. So in general, it's still not clear whether you have a smooth convergence, but certainly if fibers are not flat, the curvature cannot be bounded. Okay. So recently, based on a relative volume comparison of a Ricci flow, we have made substantial progress. Basically, we can solve this conjecture in many cases. So the first we solve the cases of complex surfaces completely. That's basically so this time it's only for elliptic surfaces. Right? So very recently, I think we are posting a paper next week, hopefully. So it's proved if generic fibers of these are flat, say tori, for example, but not necessarily tori, you can be a portion of tori, then this manifold, together with the normalized Ricci flow, has a uniform bounded diameter. So they converge to a compact metric space, which is a completion of this, okay, metric, which give a completion. So it almost solves that conjecture, except we still need to identify Z with M canonical globally. We know that this limiting metric space is a metric completion of this part, but still we need to identify as the whole thing as a canonical model. So we can do that if we assume a M canonical is smooth or is an obifold. Then this is done in the same paper. So here I should say it's in using this our relative volume comparison theorem. If I still have this recorded here, it's so there's a Ricci curvature condition for initial for this on this parabolic ball of Bx this part, and this condition is automatically satisfied. This is due to work of this Feng and Zhang. They had some idea, but actually the actual proof was done by Han and Tosadi. Okay, so Han was my former student. So Ricci curvature, this condition is satisfied if fibers are flat. In general, it's still a conjecture. We conjecture this condition is actually always satisfied on this part. So that involves certain Hessing type estimate for complex Monchon-P type equations. Okay, and also to prove the previous theorem, we need to use this use the result of Song and his two students, and that's they actually proved the metric on the twisted canonical metric on this part. I construct with Song actually has a finite diameter. Okay, so bounding a diameter is one of very crucial steps in studying this geometric convergence. Okay, so so maybe I say remarks on maybe I just skip this. So now let me say a few words about the proof for relative volume comparison. So first, let me recall this compact Riemannian manifold, okay, and recall this W functional, which I already said before, okay. And then we plot in this U in this form, so that's you get a different form of this volume comparison theorems. Not volume comparison. These W functionals, okay. So now we let omega any bounded domain in M, we define a local entropy. Okay, so this is almost same as essentially the same as Perelman did, except we we consider domain, and we require this function u to vanishing on the boundaries. Vanishing on the boundaries. That's that require u to have a compact support. This 0 means that. Okay. So when M has no boundary, of course, it's back to Paraman's original entropy. Okay. So what is and this local entropy already used by Zhang Qi and Bing Wang in their works. So what's our starting point? So we made the following observations. In some sense, it's not totally surprising because that's somehow built in a Paraman's work is the entropy. Low bound of entropy is related to these volume ratios. Okay, so we prove the following things. If you take a geodesic ball of radius 2r, and this is for any matrix. Okay, so it's just some general facts about entropy. Now, if this Ricci curvature bounded from below at this order, as I said, all these r like this is just make it a scaling invariant. And to be simple, you can simply take r to be 1, for example. Okay, so then we can bound the volume ratio from above in terms of entropy, low bound of entropy, low bound of entropy. Okay, so this is the first lemma we proved, and then secondly, we found conversely, if a scalar curvature bounded from below, so scalar curvature is bounded from above instead of so previously we said Ricci curvature bounded from below. So this time, and the volume ratio is bounded from below by this local entropy and on this ball. Okay, so from here you can roughly see what the proof is. So we know the scalar curvature in our case, at least we assume the scalar curvature here is bounded. Okay, so we assume scalar curvature here is bounded. That's actually in application is always true, even globally is true. Scalar curvature is bounded from above. So we can so volume ratio here is bounded from below by entropy. By entropy. Okay, it's a little bit complicated. I have to plot this to take infimum of entropies in the certain time range. Okay, but anyway, roughly speaking, the volume here, volume ratio here is bounded from below by entropy, and then here, and volume ratio by previous theorem is bounded from above. That's this is time. The time here is after this. Okay, so then you think, okay, if in the Paraman case the entropy is monotonically increasing, right? So then the entropy here should be bigger than entropy here. You're done, right? That's what the Paraman did basically. So, however, this page is basically we try to imitate what the Paraman prove the monotonicity of entropy, but the life is not that good. Is in the local case, in the local version, we don't have exactly the monotonicity. Okay, so what we have is what you can do. You imitate the proof. You look at like minimizer of this entropy on this ball, okay, on this ball, and minimizer exists. You just imitate what the Rathaus proved, and there's a minimizer for logarithmic inequalities. So in this case, and then you're solving a backward heat equation. This is backward heat equation, and with the initial data, with the initial data, because you solve from time 1 backwards. Okay, so then you plug into this, you play around, and play around using these solutions, and play around with entropies and so on. I skip some of these detailed computations. What you get is the following. So this is the entropy at a later time. It's bounded from below by entropy at the bounded from above. Sorry. So the entropy at this time is bounded from entropy at a later time by this. Okay, but if you don't have this term, that's exactly a monotonicity of Paramat. But however, in the local case, you have this bad term here. It's bad term here. Okay, and recall this VT is a solution of backward heat equations, backward conjugate heat equations, and the even worse is this appears in the low bound, right? It's the inverse of this integral. So this is so far the best you can get for this local entropy, and maybe I mean, at least this is what one can get for this monotonicity. Okay, so that's why we call it only a partially monotonic, modulo this term. Okay, so we need to control this term, and the controlling is it's highly non-trivial to control this term, because for people who studied the heat kernel before, or study elliptic equation or parabolic equation, most time it's easier to control upper bound of some integral than controlling a low bound. So this time we really need to control this d. We need to control this from below. This region GT. Okay, so from below. Okay, so this took us quite a bit of time to do that. So anyway, so this is a little bit different form of this monotonicity. So that's don't worry about that. So then the key things we need to do is we have our conditions here, okay, and we want to I guess this. So basically we want to I already said about this volume ratio. So basically we want to do is to control this from below. Okay. So this to do this we need to do following. We need to consider this heat kernel, and which is first this is heat kernel to conjugate heat equations, satisfy this. Okay, and with initial condition. So that's and also then forward, we use this equation. Okay. So that's kind of heat kernel. Okay. So this time is different. Is we have to be compatible with Ricci flow. So Laplacian here is depends on time t, and because of this the Laplacian depends on time t. This conjugate of this flow has some curvature contributions. Okay, so we look at this heat kernel, and so then we can express any solution. So this is standard, right? You can express any solution in terms of these kernel functions, okay, and certain initial time. Okay, so certain initial time. So here I look at the backward. So initial time is at time 1. So in order to bound this low bound, we need to so suffice to prove a low bound for conjugate heat kernel. Okay, so this integral here. So this is what we proved. Okay, technically we proved, and above assumptions, there's some time, and this heat kernel bounded from below by this volume here. Anyway, this probably is a little bit too technical. So let just indicate what we do. So we do have a lot of, in the geometric analysis, there are a lot of heat kernel estimate. But there are before it's just using the cases when for the Ricci flow for this, and this is some fixed metric, and the condition Ricci curvature is say bounded from positive. Okay, so we need to adapt those estimate to our case.
And the estimate you get in the end is the same type, 1 over volume of the Euler square root.
Pardon?
Square root t. But the estimate you want to get in the end is the same type that you.
Same type.
1 over volume of the Euler square root.
The same type. Yes. Yeah, but it's because you don't have that kind of clean curvature conditions. The estimate is more technical, and yes, the scale is to be the same. Yes. Yeah. So first we basically first you do integral estimate, and what you do is you use the Li Yao and Qi Yao arguments. So this is kind of comparison arguments. Basically, you want to look at the beginning. Remember, I erased this for volume comparison theorem. The Laplacian of distant functions bounded from above by n-1 over r. So there's a parabolic version of that. Of course, this time you don't have quite the curvature conditions as you assumed before, but you just pretend the Ricci flow. Look at the space-time, like it's more like a Ricci flat case or degenerate Ricci flat. It's make a kind of this comparison. Okay, so you have these kind of things, and only things here is a lot of these things here. The constant is kind of bad because in their case, because of curvature conditions, you have more precise constant over there. But and then use this comparison, you can to compare with transplanted heat kernel from Euclidean space, you can get some low bound estimate. So that's basically an integral bound. Okay, so then you still need to do some Harnack type inequalities, and so this is we do for and we used some Harnack inequality from this Zhang Qi and Guang as collaborator. So this is for conjugate heat equations. So here is a Harnack inequality we used, and you see here is it's not optimum. So for example, here is right things here is it should be n over 2, m over 2 here. Okay, so it's not as good as in Li Yao's case. Hopefully later on you can get a better bound. But this is we found this is eventually is sufficient for us. So we then need to use this Harnack inequality to get a pointwise estimate. We need this first estimate this heat kernel when near the diagonal, when the xy is close to each other. So this basically use the previous Harnack inequalities. And then we estimate heat kernel when the xy are far from each other, are not close to each other. So this time, second case is this we need this certain argument from Perelman in his first paper in section 8. Namely, you want to see in a Ricci flow case, you can bound kind of distance functions in the and rather weaker curvature conditions. So after that we can complete the proof of this flow. So all I want to say is the large part of proof of our volume comparison theorem is to establish this low bound of integral. Thank you very much.